Hey guys, so we're going to go ahead and continue on looking at derivatives and differentiation, things like that. And what we're going to do today is talk more generally about a couple of different things. To start though, let's just quickly refresh ourselves with the first and second definition of a derivative. The sort of theory behind this we have already talked about many times, both in pre-calculus and now in calculus. And we've come to some conclusions. That is that if you were to take the limit as h approaches 0 of f of x plus h minus f of x all over h, that would give us a derivative or the slope of some tangent line. And similarly, if we had the second definition, we would have the limit as x approaches c of f of x minus f of c over x minus c, which would similarly give us the slope of a tangent line. And I stated in the past that we sort of use these in different circumstances. And so today what I want to do is elaborate on what those circumstances might be. And then in addition to that, we might talk about some other things surrounding notation and differentiation more generally. So to start, what we're going to do is just sort of determine maybe why we would use one versus another. And I'm going to go ahead and start out with the first definition. The first definition, I would say more generally, we use to find the derivative of a function, generally speaking. So in other words, if we had the function f of x equals x squared, and we were asked to find f prime of x, I might choose to use the first definition of a derivative. Now, anyone who's got experience with calculus will, of course, laugh at this lecture because later I'm going to change our procedure completely. And you'll understand what I mean by that at some point. But for now, we're going to have some torture to deal with. To find f prime of x, which is, of course, notation for a derivative. We've talked about this before. What I'm going to use is one of the definitions, in this case, the first definition. So f prime of x, which is, of course, the slope of a tangent line. In this case, we're going to represent as the limit as h approaches 0 of f of x plus h minus f of x all over h. And so what am I going to do here? Well, I'm going to have to plug in the information that I have and know f of x is equal to x squared, right? So the limit as h approaches 0, f of x plus h is simply where x plus h is substituted into the function. In this case, that's going to be x plus h squared, our input squared, minus f of x, which is the function itself, x squared, all over h. H, remember, is just the hypothetical distance between the 2 points, so that's never going to be something that we change in this circumstance. To simplify this out, we are going to need to sort of expand that first piece. So we're going to have the limit as h approaches 0 of x plus h squared. X plus h squared, you'll of course remember, is just x plus h times x plus h. Please don't distribute the exponent. When we do that out, we get x squared. We get 2xh, and we get h squared, all subtracting the x squared on the end, all divided by h. And so there's that. And then what we're going to do now is just try and simplify this. We'll have the limit as h approaches 0. Notice that the x squareds are going to go. That's going to leave us with 2xh plus h squared all over h. And I would say that generally what we're going to try and do with this first definition is get rid of the h in the denominator. Obviously, if you were to try and plug in this value now to solve the limit, it's still going to be undefined. Usually that occurs by factoring an h out of the top, which I believe we're going to be able to do here. Notice that we'll have h pulled out of the top would give us 2x plus h all over h. This is still the limit as h approaches 0. Those h's are going to cancel. And ultimately, after that, we'll be left with this limit. The limit is h approaches 0 of 2x plus h. Remember that the limit here is h approaches 0. So when we plug in at the end here, we're plugging in 0 to h. We're not going to modify x here. So we'll plug in 0 to h, and what we're going to be left with is just 2x. So our limit has produced a function rather than a specific value. In the past, we typically produce specific values. Ultimately, we think back to what we were finding here. What we found here was f prime of x, right? f prime of x we're saying is equal to 2x, which is of course also just another name for the slope of a tangent line. Though I think you'll recognize that we found the slope of a tangent line as an equation rather than as a specific value. In the past, if we had like m tan is equal to 5, what that would mean is that the slope is equal to 5 at that particular point. But notice we didn't find the definition at a particular point. We just found it for the function f of x equals x squared. And so what does that mean? Well, if you think back to what it means really is that we found an equation for the slope of the tangent line for any value of x, right? So knowing that m tan equals f prime of x equals 2x tells us, for instance, that we can use this equation to find the slope at any point. So if we wanted f prime of 2 or if we wanted f prime of negative 1, we could simply plug in those x values now into the equation that we have, and we could find that the slope at x equals 2 is 4, or we could find that the slope at negative 1 is negative 2. And we could do that for any value of x. So this first definition is actually quite useful because it gives us an equation to find multiple slopes at the same time, rather than just one single slope, which is what the second definition would give us. And we'll show that in a second. In addition, this is just a lot more useful for finding general derivatives or differentiating generally, but you'll see that for other functions, this is not going to be super easy. This is a nice situation. We're dealing with a polynomial. These situations tend to work out kind of nicely, but that's not always true. That said, let's look at the second definition for a second and how that would be different. The second definition, we state the limit as x approaches c of f of x minus f of c over x minus c. So when would we use this? Well, we can really use this in a variety of different circumstances, but let's just say we wanted to take the function x squared and find f prime of 2. In other words, we just wanted f prime of 2. If we're being forced to use a definition and we're asked about a specific value, I might choose to use the second definition instead. The simplification of it tends to be just a little bit simpler. Simplification tends to be simpler, tends to be easier, and it gives us a specific value at the end. So in this case, if we take our limit, x approaches c, our c value happens to be 2. Our f of x is x squared. Our f of c would be the y value at 2, which is, of course, 2 squared, right, or 4. So we've got x squared minus 4. And then x minus the c value, or x minus 2. You can already see that this is going to be a lot more quickly solved because you can see that the top can be factored. You can see that a part of that factor is going to cancel with the denominator. And then we're going to be left with the limit as x approaches 2 of x plus 2, which when plugged in is 2 plus 2, or 4. So it doesn't involve sort of a lot of the larger expansion and simplification as the last example, but notice that what we found here was specifically f prime of 2, right? We found one slope. We found that the slope at x equals 2 is 4. In other words, on the graph, f of x equals x squared at the point 2, 4. There's a slope there, and the slope is 4. Right, f prime of 2, slope of the tangent line at x equals 2 for f of x equals x squared is 4. We can't use this definition to find any other slope other than a single slope at a time. That's why it's sort of inefficient. However, if you're being asked in a problem to find one specific slope rather than many slopes, then it tends to be more in your favor to use this definition. I will say right now, however, you can use either definition for either type of problem, but in general, we tend to strategically choose certain ones for certain problems depending on the circumstance. I do want to make some other notes about differentiation quickly, and just before I get into this next example, I just want to reiterate some things. When we're differentiating, right, which is the process of finding a derivative, right? So our process of finding a derivative. We're finding the slope of a tangent line always, even if that doesn't appear to be the slope of a tangent line. It could be a value, which would be the actual slope, or it could be an equation, which could be used to find multiple slopes. The slope of a tangent line, a lot of the times, is denoted as f prime of x, right? This is one notation which we use. So a slope of a tangent line is f prime of x, so the first derivative. We can also see this written as y prime, right? So f of x is typically viewed as the output. So y could be viewed as the output, y prime. And then we also see it as dy dx. This notation will be quite useful, especially later on with other types of differentiation. And so just I want to make note of these things now so that when I start going back and forth between the notations, you're not confused by them. If you see m tan, if you're being asked for the slope of a tangent line, if you see f prime of x, if you see y prime, if you see dy dx, we're finding a derivative in all of these circumstances. Now, graphically speaking, we've talked about, right, differentiation as this idea, right? So you're looking at a function and it doesn't matter what that function is. If you want to find the slope of any tangent line, so let's say there was a tangent line here, or there was a tangent line here, or there's a tangent line here, in order to find the slope of these tangent lines at this value, at this value, at this value, you have to find a derivative or differentiate the function at some specific x value. It's important to note, though, that it's not always possible to find a derivative. In other words, there are non-differentiable functions and points on functions which are non-differentiable. So I just want to quickly look at a couple examples in which that's the case. One example would be a circumstance in which the slope at a specific point simply is not defined. If you look at this graph here, I've drawn a very sharp, hard corner at, let's just say, this value a here. And we'll just call this f of x. At this hard corner, the slope is not able to be defined. Notice that there's a very clear way of drawing the tangent line here as it is. You could also have drawn a tangent line here at the apex or maximum of this curve. This slope here would be 0, just so that you sort of understand that slope would be 0. This slope here at the hard corner is not able to be defined. The reason for that is that the slope just before and just after it are very different, whereas the slope before and after this point are the same, right? You can define it at that point. Another circumstance in which you would state that the function is not differentiable would be a situation where you have maybe a piecewise function and the graph doesn't have one specific slope. So if you tried to find the slope at A, that would be difficult because it's not continuous at A, right? The slope from the left and the slope from the right are different, and you can evaluate the slope from the right and the left separately if you wish, because they're defined by separate functions, right? This is definitely a piecewise function, but it's important to note that it's not differentiable there. There's no slope there. And lastly, there's a circumstance which is a little bit different and definitely comes up with the AP board quite often. That would be a circumstance in which you have a function where the slope is so steep, like so, that we would call this little area as having a sort of vertical tangent. Vertical tangent meaning it's directly up and down, if you will. From Algebra 1, you might think about this as the vertical line test. In other words, the slope here is undefined, right? The slope is undefined. It's not 0. It's so steep that the slope is undefined. It essentially is a vertical tangent. That said, it would seemingly fail the sort of vertical line test that you might remember from Algebra 1. But in this case, what we're thinking about it as is simply that there's no slope there. There's no slope defined, and thus it's not differentiable at that point. These are 3 circumstances which you need to be aware of and are useful for you to be aware of. That said, let's go ahead and look at some examples in which this is useful to remember. One really common example would be f of x equals the absolute value of x. This is really commonly talked about, a circumstance like this. F of x equals the absolute value of x. Everyone remembers this graph for some reason. Everyone remembers it as a v. And of course, the generation of its graph is pretty simple. I'm not going to plot too many points, but you know that it's essentially the absolute value of all the negatives. It looks like this. And as you can kind of see, if you look at x equals 0, just before x equals 0, there's a specific slope. That slope is -1. And just after is +1. I know that because this is a line, of course, and this line is defined by just f of x equals x. But in addition to that, we have to remember that an absolute value function, right, is actually a type of piecewise function, right? F of x equals the absolute value of x is really defined by a piecewise function. Specifically, it's defined as negative x if x happens to be less than 0, and positive x if x is greater than or equal to 0. And so, in other words, if you were to plug in any negative numbers, they'll become positive. If you plug in any positive numbers, they stay positive. And so, finding the derivative of something like this, or the slope of something like this, can be more complicated because you end up having two pieces to deal with. Now, let's go ahead and just take a look at the derivative of this graph. Now, the derivative of this graph, if I were to try and find f prime of x, I suppose I shouldn't put it there, excuse me. If I were to try and find f prime of x, what I'd have to really do is I'd have to differentiate this, and I'd have to differentiate this separately. And we'll do that at some point and look at the rules associated with that. But instead, I'm just going to show you what the derivative looks like and tell you something about it. I'm going to tell you that the derivative looks like this. Oop, that's supposed to be straight, even though it's definitely not straight. We've got a constant function at 1 from 0 on. We have a constant function from -1 this direction. And I suppose I should have, I think I put in my original, there we go, an equal sign, but we don't really need to define it at 0 here. Oop, and now I got rid of that. Maybe I'll make that straighter. You'll note that if we look at this graph, clearly f of x equals the absolute value of x has a hard corner, like that first graph that we just looked at. What that means is that there's no slope there, right? It's not differentiable at 0. And you can see that kind of on our graph here. There's no y value at x equals 0 on f prime of x's graph. You'll also notice that the slope, because this is a line, because this is linear, is equal to 1 from 0 on, right? And you'll notice that my y value is equal to 1 on f prime of x this direction on. And if we go this way, we've got a slope equal to -1 out to infinity, which is why this line is extending on a constant function at -1 out to -infinity. In other words, what I'm trying to show you is that there's a connection between f of x and f prime of x, and you can see that on the graph itself. In addition to calculating algebraically, you can see that the slopes and the y values are connected on these two graphs. The slope of these are the y values of these. The slope of these are the y values of these. That connection is very important and something that we're going to talk about quite a bit. And this is just the first time I'm mentioning it. Let's look at another circumstance in which that's the case. And we'll just compare two graphs to see that that's the case. And we'll do so a little bit methodically really quick. We're just going to do a small boom, boom, and let's say boom. And then we'll put some corresponding graph down here. Most important part about these graphs that you're drawing, by the way, are that we have these slopes equal to 0. Slopes equal to 0, slopes equal to 0, slopes equal to 0. And then in addition to that, I'm going to go ahead and generate another graph. We'll call this A, we'll call this B, we'll call this C. And say A, we'll say B, we'll say C. And then, because I'm doing this on the fly, I need to look at what I'm doing. Let's see. Let's see. Boom. Boom. and then boom, and then boom. It'll look something like that. All right. So here we've got two functions, right? I'm going to call this f of x. I'm going to call this f prime of x. Now, how did I just draw those sort of randomly? Well, the first thing I did for f prime of x is I drew this little structure, and I specifically made the slope equal to 0 here, the slope equal to 0 here, and slope equal to 0 here. In addition to that, I also decided to change up some things. So let me just make a couple notes about how these graphs correspond. First of all, you can see that at a, b, and c, the slope is equal to 0, right? It's flat. Slope's equal to 0, slope's equal to 0, slope's equal to 0. Now, the curious part about its derivatives graph is that at a, b, and c, it has a y value of 0. That's the most important part, the most curious part about it. Now, that's cool enough, but let's also analyze the slopes around these values. So if we look over here, we can see that the slope is negative, right? It's decreasing, it's going down. Here, the slope happens to be positive. Here, the slope is looking negative to me, and here the slope is looking positive, right? Now let's check out what's going on this graph, and let's see if I did it correctly, because of course I just did this off the top of my brain. The slope happens to be positive here, right? Well, the slope is positive. Excuse me, I'm totally off now. The slope is negative here, and guess what? The y values are negative here. After a, the slope is positive, and after a, the y values are positive. After we hit b, the slope goes back to negative, and the y values go back to negative. And after we pass c, the slope goes back to positive, and the y values go back to positive. So this connection is super important and something that we really have to pay attention to as we're discussing these things. And later, this will become even more sort of drastic when we start talking about other types of functions. All right, so let's just look at one last thing and try and sort of put all this stuff together. Let's just choose some specific example to talk about. And I think the easiest thing, I have no idea what example this is, would be f of x equals x to the third, because polynomials and their derivatives are pretty easy to find. So how are we going to look at this? Well, let's just start by finding the derivative of this function. So let's find f prime of x. Now, how difficult is this going to be? Well, it could be very difficult. It's kind of annoying to do if we use the first definition of a derivative. And so I'm just going to use some shorthand, what is really a power rule, but I haven't taught you yet because I just want to show you the connections. So if f prime of x, I'm going to just tell you is 3x squared. And I guess I could also tell you that the second derivative, if I were to take the derivative of this, f double prime of x, would be equivalent to 6x. How I just did that quickly, I'm sure you can figure out. If not, you've already probably looked up because you hate using the definition of a derivative. But I just want to look at these graphs in order to make connections. So f of x equals x to the third. We all know what that looks like. We've probably graphed it a bajillion times. It's got a point at 0, 0, a point at 1, 1, and a point at 2, 8. And it looks something like this. Now, my graph does not fully accurately show everything here, but there's some things to show. And one of those things is that my slope at x equals 0 should probably be a lot flatter. But we'll make that note in a second. So we've got f of x equals x to the third here. Let's look at the next graph, which would be f of x equals 3x squared. This is, of course, our f prime, right? And then we'll look at our last graph, which is just a simple f double prime of x equals 6x. So 3x squared, we go up by 3. There we go. And then finally, over here, we're going up by 6. All right, so obviously I'm telling you that these are derivatives of each other. I'm telling you that this is our original, this is the first derivative, and this is the second derivative. Now, what are we going to make judgments about here? Well, you can see some things, right? For starters, you can see that the slope of f of x equals x to the third is positive. It's positive here. It's positive here. It's positive here. It's positive here. It doesn't seem to be negative anywhere. In addition, like I said, my graph is a little off, but this graph should really flatten out somewhere around here. In other words, the slope should be equal to 0 at the origin. I would have to graph my function here very accurately, which of course I'm not doing on this whiteboard, but I'm telling you that the slope is equal to 0 there and that the slope is positive everywhere else. Now let's see if we can make that connection on its derivatives graph. Well, if the slope is equal to 0 at 0, we expect that the derivative should have a y value equal to 0 there, and it seems to, right? In addition, before it, the slopes are positive, and after it, the slopes are positive. So before it, the y value should be positive, and after it, the y value should be positive, right? These are y values here, y values here. We're talking about slopes here. We're talking about slopes here. Do you see that connection? Hopefully you see that connection. Well, we could also make the judgment between these two, right? If you look at this graph, right, and this is going to be harder because I've got some stuff written on it, you can see that the slopes are negative here, and then they seem to zero out at 0. And then the slopes are positive, right? It's decreasing, it's 0, it's positive. Well, at 0, it should be 0. It looks like the y value is at 0 there. The slopes are decreasing, the slopes are negative. Look at that. The y values are negative here. After 0, slopes are positive, increasing. Look at that. The y values are positive. Seems like the connections that we're making seem to be true for both these two and also these two, right? Now, I will say that there's also, not only is there a connection between these two and these two, but there's also a connection between this graph and this graph, which is a little bit harder to make. And that connection has to do with something called concavity. But we're not going to talk about that just yet. What I can say is that where these y values are positive, our graph will be concave up, versus where these y values are negative, our graph will be concave down. But that refers to a second derivative and some other things, which we'll talk about a little bit later on. I don't want to get too much into that. In any case, this is just a quick dive into differentiation and what it's going to lead us to. And so I'm going to go ahead and stop there.